Welcome everyone to the first What is Talk of the semester. And today we have with us Professor Kaneenka Sinha, who is an Associate Professor of Mathematics here at IISER Pune. Professor Kaneenka works in analytic number theory, and today she'll be talking to us about additive number theory. So you can start.
Okay. So thank you, Aniket and Varun and Maths Club for the invitation. So we have been, and thank you to all of you who are here for the talk. So Maths Club and I have been corresponding about this talk for a while now. And we kept, so after the talk by Professor Raghuram a couple of semesters ago on what is number theory, we were interested in doing a follow-up talk and we kept discussing. So first we thought maybe we'll do a talk on analytic number theory, then the plan was to give a talk on probabilistic number theory, then it changed to additive number theory, and we've been going back and forth. But all said and done, today we'll talk about additive number theory. I have taught this course here as a topics course 2 times, and some of the members of the audience have attended these lectures. So, but I hope they will also learn, get to learn something new from a refreshing perspective. So on this note, let us start. Okay, so as we all know, so any course in number theory starts with prime numbers, which are the building blocks of numbers. So what does that mean? So prime number is a natural number greater than 1, which is not divisible by any natural number other than 1 and itself. So we all know what are prime numbers. We know several nice properties of prime numbers. So for example, the fundamental theorem of arithmetic states that any natural number is either a prime or can be written uniquely as a product of powers of primes. We also know that there are infinitely many prime numbers, right? So now the question is, suppose I take a finite number, C, let's take 100. And let me ask you, can you write any n greater than 1 as a product of at most 100 primes? Okay, and you are allowed to take very, very high powers, as high as you want. But the question is, so given the vast choice of powers, but only finitely many primes, can you write any n as a product of at most c number of powers of primes? And immediately you see the answer is no, because what you can do is you can take the product of the first 101 primes, okay? And because of the fundamental theorem of arithmetic, you know that this product cannot be written as a product of primes in any other way. Okay, all these primes, distinct primes, are important components of n, and neither of them can be ignored, right? So therefore, the answer to our question is no. Now we give an additive spin to this question, and we ask, so before that we make an observation. Any n greater than 1 is either a prime or can be written as a sum of prime numbers, though not uniquely. Okay, so for example, 10 can be written as 3 plus 7. It can be written as 3 plus 5 plus 2, or it can be written as 2 plus 2 plus 2 plus 2 plus 2. In general, any number, you can keep adding 2 with itself many, many times because you are allowed repetitions. When you're writing anything as a sum or a product of prime numbers, you are allowed repetitions. So you can just, let's say your number is even, you can just keep writing 2 as many times as you want. Okay, so prime factorization in the additive sense is much easier. On the other hand, if your n is an odd number, you can just keep adding 2 to itself until only 3 is left over, and then just add 3 to the last, as the last bit. So this gives you representations of any number n as a sum of prime numbers. And now we can ask the same question that we asked for products of primes. Let's take a finite number c. Can we write any n greater than 1 as a sum of at most c primes? For example, can we write any n as a sum of at most 100 primes? Okay. So in this context, the famous Goldbach conjectures were made by Goldbach in 1742. And they're extremely interesting because they say that you actually don't need that many primes to build up all the numbers, okay, when you're putting them together additively. So Goldbach binary conjecture says that every n greater than 2 is exactly a sum, can be written exactly as a sum of 2 primes. Okay, this is also called the strong conjecture. It is still an open problem. It hasn't been proved. Now notice we were very careful here. We were taking every even n strictly greater than 2. Okay, because when you take n equal to 2, that itself is a prime. So the same conjecture can be rewritten as every even n is a sum of at most 2 primes. Okay, and here we are only talking about natural numbers. So this perspective of at most is useful for us when we express these problems in a more transparent mathematical language. Okay, the weak also, whenever if there's a strong conjecture, that means there's a weak conjecture floating around as well. So this is the Goldbach ternary conjecture. And what does it say? That every odd n greater than 5 is a sum of 3 primes. Okay, and so we seem to have ignored 5 and 3 themselves because they are primes. So another way of stating the Goldbach ternary or the weak conjecture is every odd n greater than 1 can be written as a sum of at most 3 primes. Okay, now why is this called the weak conjecture? It's because the strong conjecture implies the weak one, but not vice versa. So any odd n greater than 5 can be written as 3 plus k. You can observe this immediately, where k is even and it is greater than 2. So if you knew a Goldbach decomposition for k, then so you have written k as a sum of 2 primes, p1 plus p2, and 3 is the third prime. So this proves your ternary conjecture. So the journey to, now the ternary conjecture, I'm happy to inform you, has been proved. It was proved very recently by Harold Helfgott in 2013, and we hope in this talk to survey the journey towards Harold Helfgott's work. Okay, so so how did it all start? What were the initial results in this direction? So in the 1920s, Hardy and Littlewood proved the ternary Goldbach conjecture, not for all odd values, but for sufficiently large odd values of n. So when you are stating a theorem with respect to these additive problems, there are many steps to the main theorem or the main conjecture. So the question is, even if you can't say that every n, so in order to show that every n greater than 5 is a sum of a certain number of primes, what you could do is perhaps some mathematical method would tell you that every odd n greater than or equal to c can be written as a sum of 3 primes, and then between 5 and c you can just check it manually. Okay, but that is a different problem altogether and very hard, but we have to use both the approaches to prove ternary Goldbach. And also the other limitation of the result of Hardy and Littlewood is that it is not unconditional. It is assuming something called the generalized Riemann hypothesis. Okay. In 1937, okay, Vinogradov proved the ternary Goldbach conjecture unconditionally. But again for sufficiently large odd values n greater than or equal to c. He did not specify what this c is, but he said that if n is sufficiently large, you can, a proof of Goldbach conjecture. That Goldbach conjecture holds for those n. Okay, so that means at least you know that for almost all n, odd n, this is true, but then effectively you do not know the value of c. Okay, so the first value of c came in 1956 by Borodkin, who in fact, this was his PhD thesis. So he showed that 10 raised to this humongous 7-digit number, okay, it can be written as can be written as a sum of 3 primes. And therefore, he reduced the Goldbach conjecture, the ternary Goldbach conjecture, to simply verifying it for all the odd n less than this explicit C. Okay, but it's not that easy to do it. I'll mention the computational issues involved, but as things progressed, in 1989, another work was published by Shen and Wang, who reduced C to a slightly smaller power, but it is still a very, very large number, 10 raised to the 43,000. And in 1996, this was further reduced to 10 raised to the 7,194. Now, in 1997, Desuyer, Effinger, Terriel, and Zinoviev proved the ternary Goldbach conjecture for all odd numbers again, but conditionally on GRH. So their result was an improvement on Hardy and Littlewood's result, because they did not have this issue of sufficiently large. They do it for all odd numbers n, but they make the same assumption as Hardy and Littlewood do. So until 2013, the best known bound was by Liu and Wang, which is 10 raised to the 1346. Okay, so now of course you can ask, well, how, I mean, isn't it immediate now? We can just check it for all the values, odd values less than 10 raised to the 1346. But it turns out that on the most powerful computers, computer verification of the ternary Goldbach conjecture, which sometimes in shorthand notation we also call 3GC, it can be done up to around 10 raised to the 30. Okay, so if you can bring down your effective value of C to something less than or equal to 10 to the 30, you are fine. Then, and this is exactly what Harold Helfgott did. Okay, so essentially he proved that the ternary Goldbach conjecture holds for all odd values of n greater than or equal to 10 raised to the 27. And therefore now we can combine Helfgott's result with computer verification that has already been done up to 10 to the 30, and this proves the ternary Goldbach conjecture. So one way to understand Harold Helfgott's result is that he made Vinogradov's result effective. Vinogradov told you that for sufficiently large odd n, the ternary Goldbach conjecture is true. Okay, and Harold Helfgott gave an effective value for that sufficiently large, okay, which was useful enough, small enough for us to combine it with computer verification and completely take care of the ternary Goldbach conjecture. Okay, so now related developments. You know, when we are talking about Goldbach conjecture, we are obsessing a lot on the fact that your number n has to be written as a sum of exactly 3 primes, or in the case of even n, as a sum of 2 primes. So related developments ease this problem a little. So what they do is they take a finite number d and they ask, can we write any n greater than 1 as a sum of at most d primes? Okay, so instead of wondering whether you can write n as a sum of 2 or 3 primes, why not take a larger number? And that would also be a very useful and a nice thing to work on. So in this respect, Schnirelmann showed that such a d exists and it is effectively computable. Okay, but again, he does not tell you exactly what that d is, but he says you can find a finite number d so that any n can be written as a sum of at most d prime. Such a finite number d exists. Even making such a claim is quite a progress. In 1995, Ramaray proved that any even n is a sum of at most 6 primes. So instead of 2 that we need for Goldbach conjecture, he's able to show that it is a sum of at most 6 many primes. Okay, even we don't know about 2, whether 2 primes are enough. At least we know that at most 6 primes are enough. And in 2012, Terence Tao proved that any odd n greater than 1 is a sum of at most 5 primes. Okay, this is also a remarkable result. And you can combine both of these results to make a claim that any natural number n greater than 1 is a sum of at most 6 primes. And from there, we have to go down to 3 and 2 respectively. So now the amazing thing is that all of the above results use a method called the circle method. Origin of this method lies in a 1918 paper of Ramanujan and Hardy. So I'll mention a little more about it in detail later, but Ramanujan and Hardy were interested in exploring the partition function, which is the number of ways of writing n as a sum of smaller numbers. So you need, if not a formula, then some kind of an asymptotic for the partition function. And this was first established in this work of Ramanujan and Hardy in 1918. Unfortunately, soon after that, Ramanujan passed away. And this method was further developed by Hardy and Littlewood. Okay? So now the question is, we've provided some examples of what are called additive problems. And now it is time to put them in a bigger category of problems. So what is additive number theory? Let S be a subset of the natural numbers. So we don't just have to obsess with the primes. There could be other types of numbers that you like. For example, maybe you like squares a lot. You like to work with squares. So you would ask, can you write any number n as a sum of a certain number of squares? Okay. So is S additively sufficient to build the complete set of natural numbers? Secondly, as we demonstrated in the Goldbach conjectures, is there a finite C so that any natural number, however large, is a sum of at most C elements of S? For example, as I mentioned, you could take the set of squares. And typically, when you take a first course in number theory, the big theorem you prove towards the end of the course is that any n can be written as a sum of at most 4 squares. 4 squares are enough to take care of all possible natural numbers. And this leads to a series of questions. What if you replace squares by cubes or fourth powers? So around the same time, Edward Waring made this conjecture, and he said, every n greater than or equal to 1 can be written as a sum of 4 squares, 9 cubes, 19th fourth powers, and I'm quoting him exactly, and so on. Okay, so what does he mean by and so on? Okay, is he trying to say that irrespective of what type of kth powers you choose, you know, whether squares, cubes, fourth powers, fifth powers, and so on, can you express any natural numbers as a sum of a very explicitly finite number of kth powers? So he says that for cubes, the number 9 works. Any n can be written as a sum of at most 9 many cubes. Any n can be written as a sum of at most 19 number of fourth powers. And his claim is that for any k, you know, you can have a similar statement. All right. So this is essentially what is now called Waring's problem. And additive number theory is the branch of number theory that deals with additive problems of this kind, and it develops the necessary language to state a problem clearly and techniques to address the problem. So in this respect, for those of you who've taken my course in additive number theory, you know that we pretty much spend the entire course focused on Waring's problem. And it took us a while to even learn to state this problem precisely and develop a nice way of approaching them. Okay, so this brings us to the notion of Schnirelmann's density. Okay, we just met Schnirelmann some time ago, who had made important contributions towards the Goldbach conjectures. So what is this density? Okay, now let us take any subset of the natural numbers and let a of little n denote the number of natural numbers up till little n which lie in the special set capital A. Okay, so now you all know that the natural density of A, when we think of density, this is what we think of it as. It is essentially the proportion of elements of A in the entire set of natural numbers. So for every little n, you count a of n divided by the total number of natural numbers up to n, take the ratio, and take the limit as n goes to infinity. And if this limit exists, okay, then that limit is what is called the natural density of A. Sometimes the limit could be 0, which is a way of saying that such numbers are very, very scarce, scarcely situated in the set of natural numbers. Now, Schnirelmann's density does something slightly different. Instead of taking the limit as n goes to infinity, he emphasizes on the infimum for all n greater than or equal to 1. Okay, so the difference between Schnirelmann density of A and the natural density of A is that the Schnirelmann density takes into account very small values of little n as well, whereas the natural density is concerned with the limit for very, very large numbers of n. Okay. So for example, let us take these very elementary sets, even numbers and odd numbers respectively. So the natural density of odd numbers and even numbers, you can almost immediately verify this, is half. And this is what you would even intuitively imagine, right? That among all the numbers, they are evenly distributed between odd and even. In fact, you can, with little bit of work, you even have a precise formula for O of n, which also helps you to see what happens as n goes to infinity. So therefore, the natural density, so not the natural density, but from this formula for O of n, you deduce that the Schnirelmann density of the set of odd numbers is half. Okay, but the Schnirelmann density of the set of even numbers is not half, because E of 1, like I said, this density is very sensitive to small values of n. So E of 1 is 0. So delta of E is 0. So this is how the Schnirelmann density differs from the natural density. So in general, if 1 is not an element of A, then A of 1 is 0, and therefore delta of A is 0. Okay, now the question is, how is this relevant to additive problems? And this was Schnirelmann's big contribution. So let us take any two subsets, A and B of n. They could be equal to each other also. Okay, but let's specify two subsets of n. Okay, and let us define a notion of sums of these sets. Okay, so what we do is, we take all possible x plus y, where x is either in A or 0, and b is either in, y is either in b or it is 0. So what is the advantage of taking 0 into account? Well, in that case, a plus b is also counting all the members of A as well as all the members of B. So in particular, let us take the set of primes. Let A be the set of primes. Then A plus itself, okay, includes 0. Okay, it includes all the primes, and it includes P1 plus P2. In other words, it includes all the non-negative integers, okay, which can be written as a sum of at most 2 primes. All right. So in particular, what we do is, so we are, of course, we are only interested in the natural numbers. So 0 is just to make sure that we don't miss out individual sets A. So what we do is, any m, for any natural number m, we define m times A to be the sum set A with itself m many times intersection n. Okay, so so for example, for 2A, we will remove 0 from that set. So it is, so 2A refers to the set of primes as well as those numbers which can be written as sums of 2 primes, where P1 and P2 can be equal. So a typical additive problem will ask you whether you can find some fixed number m so that m times A, so A added to itself m many times in this kind of a sum set way, will give you the set of all natural numbers. So basically this is a more, so Schnirelmann expressed an additive problem in a very precise and a very transparent language. So can you find an m so that m times a is equal to n for some n? Okay. And Schnirelmann's theorem is, and this is also something that we prove in a typical additive number theory class, that, well, if the Schnirelmann density of a set is positive, then the answer to the above is yes. A is sufficient to build the entire set of natural numbers additively, provided you are willing to add A to itself sufficiently many times. Okay, but if delta of A is equal to 0, then Schnirelmann's approach will fail, right? Then you have to think of a different way. On the other hand, if delta of A is equal to 0, it does not mean that you cannot find such an n. Okay, so the converse of Schnirelmann's theorem is not true. So, for example, let us take, as Waring did, let k greater than or equal to 2, and let b sub k denote the set of all kth powers of natural numbers. It will not take you very long to verify that delta of b sub k is equal to 0, okay? Because you'll have a ratio of the form n raised to the 1 by k over n, okay? So that the infimum of those type of ratios would be 0. Okay? And what Linux showed in 1943, it's also another important theorem that we proved in a course in additive number theory, that, okay, fine, delta of b sub k may be 0, that's all right. But if you add bk to itself sufficiently many times, you will have a set with positive Schnirelmann's density. Okay, and therefore, this mb sub k can be added to mb sub k g1 many times to generate the set of natural numbers. So, you know, so it's like, it's all right. We don't have to be hindered by any restrictions with b sub k. Let's just add bk to itself many times. Let's keep experimenting till we hit another set with positive Schnirelmann density. All right. And then once you do that, then you can show this, that mbk added to itself a certain number of times will generate the entire set of natural numbers. And I leave it as an exercise for you to verify that g1 of mbk is exactly equal to g1m times bk. Okay. Okay, so
Ma'am, I have a doubt. So the result by Linux, is it is it biconditional, as in can you generalize it to say that if delta of m times your sum set is greater than 0, then you will always have, then it will always, so g1 of that will always give you n.
Yes, yeah, that's right. I mean, in fact, so you are saying that, so you are asking whether what we have said for b sub k would apply to any other set.
Right.
Right.
So,
no, that we don't know.
Okay.
His theorem is specifically for the kth powers.
Right. So you can have
no.
So you can have a sum set. So you can have a sum set such that m times that sum set, the delta of that is always equal to 0. But then you can still have you can still have a sum set that is equal to n.
Yes.
Okay.
Yeah. Okay.
Thank you.
So now what do Hardy and Littlewood show? Okay. What they do is, so again, in a sense, they sort of make Linux theorem a little more effective. They actually tell you that given k, if you're looking at the set of kth powers, then for any number g which is strictly greater than 2 to the k, any sufficiently large n can be written as a sum of at most g numbers of kth powers. Okay. For many values of k's, though, through other methods, you can find smaller values of g. So, for example, let's look at Hardy and Littlewood again. So, if you were talking about k equal to 2, okay, so that means for any g greater than 4, any sufficiently large n can be written as the sum of at most g number of squares. So that means for any g greater than or equal to 5, so in particular, this theorem is saying every sufficiently large n can be written as a sum of at most 5 squares. But Lagrange's 4-square theorem is already telling you that you can do better than that. You can come down to 4 squares and it takes care of all possible integers. So, like I said, for many values of k through other methods, one can find smaller values of g. But at least this is a great beginning. It tells you that such a g will exist. Now, coming back to the Goldbach problem, let P be the set of primes. Okay. Schnirelmann showed that there exists a natural number d such that d times P is equal to the set of all the natural numbers, but of course strictly greater than 1. Okay. And so now in this new language, all the previous theorems that we studied can be rewritten. So Ramaray's theorem is telling you that 6 times P is equal to the set of even numbers. Okay, Tau is telling you that 5 times P is the set of all odd numbers greater than 1. And the weak Goldbach conjecture says that, well, 3 times P is the set of O greater than 1. And the strong Goldbach conjecture is that 2 times P is equal to E. We don't even need to go all the way up to 6. So this is thanks to Schnirelmann, we have a very nice way of stating additive problems. And in fact, you take any additive problem of your choice, you will be able to write it in this language of some sets. Okay. Now, what is the circle method? Circle method is a technique to solve additive problems. So it's the foundation of this method, the founding idea, the base idea is very, very simple. So what we do is, for a real number x, we take the function e of x, which is basically the exponential of 2 pi ix. Okay, so e to the 2 pi ix, which is a complex valued function whose real part is cosine 2 pi x and the imaginary part is sine 2 pi x. Now, it doesn't take you long to observe that e of x is a periodic function of period 1. Okay. Another very elementary but very useful fact about these exponential functions is that if you integrate e of mx dx on the interval 0 to 1, then you will get 1 if m is equal to 0. And for any non-zero integer, this integral just becomes 0. Okay, you can quickly verify this for yourself. I leave it as an exercise. But this is basically at the heart of this integral identity is the reason this method is called the circle method. Okay, so why is it called the circle method? So notice that as you let x run from 0 to 1, on the complex plane, you are essentially going over a unit circle, so a circle of radius 1 with origin at 0. Okay, so for a reason as simple as that, this is called the circle method. Now let us take a natural number n and let us define the exponential sum. Okay, so now whenever I take combinations or sums of these exponential sums, I just denote them as an exponential sum. So in particular, we take exponential sums coming from prime numbers. Okay, so take some fixed natural number n and denote f of x to be equal to the sum of e of px as you run over all the primes less than or equal to n. Okay. Then what happens is, when you take the square of f, you know, why are we even writing these exponential sums? Why are they related to our additive problems? So you'll see a template which converts additive problems into a problems of evaluating integral. Okay, so we've got f square of x, which is because of the properties of the exponential function, you know, e of a times e of b is equal to e of a plus b. So you end up just writing this as e of p1 plus p2x, where p1 and p2 run over all the primes less than or equal to n. So what is this basically telling you? So now what you do is, so take your number n. Your original question was whether you can write n as a sum of two primes, p1 and p2. And those two primes obviously have to be less than or equal to n, right? So what we do is we take this function h square of x, multiply it with e of minus nx, and then integrate this function from 0 to 1. What it ends up giving you is the sum of all the following integral, e of p1 plus p2 minus n of x dx from 0 to 1, okay, where p1 and p2 run over all the primes up to n. Now, what do you know about the inner integral? The inner integral takes the value 1 exactly when p1 plus p2 minus n is 0. Otherwise, it takes the value 0. Therefore, because of that fact, this exponential, this nice integral expression coming from exponential functions is actually a counting quantity. Okay, it is recording the number of primes p1 and p2 up to n, so that their sum is exactly equal to n. All right. So maybe I can pause for a second, and in case there are any questions, people can ask me now. Okay, so Riddhi is asking, so let me just go back to a slide. What is the difference between Schnirelmann's theorem and Linnig's theorem? So Schnirelmann's theorem is a very general theorem. He's saying that if you have any set with positive Schnirelmann density, okay, then it would be additively sufficient to build the set of entire natural numbers. Whereas Linnig's theorem is specifically focused on the set of kth powers. And it is telling you, it is giving you an explicit example of a set whose Schnirelmann's density is positive, and therefore from that you can derive Waring's problem. Okay, so Linnig is actually using Schnirelmann's theorem to give a positive answer to Waring's problem. Right? I hope that is clear. So I'll continue, and then we'll keep taking questions from time to time. Okay, so the one of the most important steps in circle method has already been accomplished. We have converted the Goldbach conjecture, especially the binary Goldbach conjecture, into evaluating a certain integral expression. Okay, now the question is, so now we want to check whether the left-hand side is positive. Okay, so if you can show that the left-hand side is positive for all even n, there you go, you've got the binary Goldbach conjecture. If you can show that this is true for sufficiently large even n, that is also good. You don't have binary Goldbach in its entirety, but you have it for almost all integers, even integers. Okay, so to summarize, this now becomes our object of interest, an integral. So we convert a counting problem into a problem of calculus. Okay. To address the ternary Goldbach, we do exactly the same thing, but this time instead of square of f of x, we have to take cube of f of x. Okay, so now how do we evaluate this integral? Is it something that can be done like a typical question in your first year analysis course? Okay, and before that, of course, the intermediate question is, even if we don't know anything for these integrals for 2 or 3, before that, can we come up with some positive number d so that the integral of f to the d of x times e of minus nx dx is greater than 0, either for all n or even for sufficiently large n. Okay, so Schnirelmann said, yes, you can do this for the set of prime numbers. So again, in this language, all the previous theorems that we have studied can be restated. So what Vinogradov shows is that for sufficiently large odd values of n, this integral for cubic powers of f of x is positive. Okay, and Helfgott's theorem essentially makes Vinogradov's theorem effective. He says that for all odd values of n greater than or equal to 10 to the 27, the above integral is positive, which is what you want. And for n less than 10 to the 27, you already have computer calculations, and therefore you end up proving ternary Goldbach conjecture. So it is in this language that Harold Helfgott proves the ternary Goldbach conjecture. So if you have stayed with me this far, and if you have even understood this calculus type language to restate your additive counting problem, that is a very good beginning. I'll be okay if you choose to now go to sleep for the rest of the course, for the rest of this lecture. Now, key steps in the circle method. We still have to evaluate the integral, right? So the most fundamental observation in the circle method is that this function, this exponential sum that you have to square or cube and then integrate, it peaks. It takes very, very high values at rational numbers, okay, with suitably bounded denominators, okay? So this looks very abstract and strange. I mean, how do we even know this, right? So we will have to do some experimentation. So I'll come to it in a slide or two. But basically what we do is, once we classify those points on the circle where this function takes very, very high values, we take small neighborhoods around those points, very, very small, and we remove them. And those are called the major arcs. Even though actually the length of those intervals that we are removing is very, very tiny, but they are going to account for the major contribution to the integral that we are looking at. And whatever is left over are called the minor arcs. Okay. So now let us take, so even before doing the major arc, minor arc differentiation, let's try to evaluate the function at certain values of x. So let's take x equal to 0 or x equal to 1. So you have e of p times 0 or e of p times 1. They are both equal to 1 for each prime p. Therefore, f of 0 and f of 1 is the set of all prime numbers up till n. Okay, so now what if you go a little further? Let's take another rational number, and let's just keep increasing our rational numbers in a very systematic order. Okay, so 0 and 1 can be thought to be rational numbers with denominator 1. Now let us consider rational numbers with denominators 2. Okay, so you've got f of half. F of 2 by 2 has already been done, which is f of 1. So f of a half, what happens? You have e to the 2 pi I pi p over 2. Okay, so which is e to the I pi p, but e to the I pi, we know by a theorem of Euler, that is just -1. And you raise -1 raised to the p. Okay, and since almost all the primes are odd numbers, basically this is just giving you something which is very close to minus pi of n. Okay, we don't have to worry so much about the signs because we are just trying to understand the size of these functions. So we are more keen on the absolute values. So this also, the absolute value of f of half is of the order of pi of n. Right? What happens now if you change 1 by 2 to 1 by 3? Okay, so here what we do is we observe, so we have to calculate e raised to the 2 pi I pi by 3. Okay, and because of the fact that your exponential function is periodic of period 1, okay, you can actually, instead of doing it for all the primes, you can reduce primes modulo 3. So you can write p to be 3l plus r, where r is the remainder left over when you divide p by 3. Okay, so it can be either 0, 1 or 2. The case r equal to 0 can be immediately thrown away since p is a prime. So r cannot be 0. Otherwise, p would be equal to 3 times l. Right? So what we have to do is, when you are talking about values of exponential functions, in this case, essentially, you can reduce it to the problem of evaluating these functions at certain residues. In this case, the residues are 1 and 2. And then for each r in the inner sum, you count all the primes which are congruent to that r mod 3. Okay, now, if you remember Raghuram's talk, and even if you don't remember, we'll just review this. So this was a theme that is a very, very fundamental theme in number theory, which is the existence of primes in arithmetic progressions. Okay, so basically what we know is that if you consider all the different residue classes mod 3, and then you take the box of all primes and just keep throwing them into their appropriate residue classes, this box will eventually get evenly distributed among all the residue classes. Okay, particularly the non-zero residue classes or the co-prime residue classes mod P. So because of that, for each R, the number of primes that is congruent to R mod 3 is basically the total number of primes divided by the total number of non-zero residue classes, non-trivial residue classes, which is given by the Euler's phi function, phi of 3. Okay, so this is giving you, so you've got f of 1 by 3. It's approximately of the size of pi of n over phi of 3. By the way, I'm emphasizing on this approximation. You must remember that this is not an exact value. Okay, so for up till any n, this contributes to the major contribution to the value we are looking at. And then there is an error term, which will be of smaller order than pi of n. And it is in the evaluation of such error terms that heavy duty techniques like generalized Riemann hypothesis, etc., come into the picture. Okay, but this talk focuses mainly on first principle, so you don't have to worry too much about the technical details. So we are still on the order of pi of n with the finite constant attached to it. Okay, now you can do exactly the same thing for any rational number of the form 1 by q. Okay, you can take all the residue, all the non-trivial residue classes mod q, or the co-prime residue classes mod q. Okay, and in the inner sum, you calculate all the primes, the number of primes which are congruent to each of these residues mod q. And exactly as we did for q equal to 3, we end up getting pi of n over phi of q, which phi of q measures the total number of co-prime residue classes mod q, times the number which either takes the value 1 or minus 1, depending on how many odd prime factors our number q has. Okay, and this, in fact, it turns out that if this number q, if it is square free, that means it can be written as a product of distinct primes without any higher powers, then this would take the value 1 or minus 1. But even if one of the prime factors appears to the power of 2, then this value just becomes 0. Okay. Now notice in this, just let's look at the final expression. Okay, for every, as the denominator q keeps growing, okay, the denominator phi of q will also keep growing. All right, so in terms of absolute values, 1 over phi of q will go to 0 as q goes to infinity. Okay, so when that means for those numbers 1 by q with very, very high denominators, high values of denominators, the function will take very, very tiny values. So that is the reason why we are interested in those rational numbers where the denominators q are bounded enough, okay, to take us to something reasonable. Okay, the other important point is I've so far only been focusing on rational numbers with numerator 1, but the same thing can be carried over to any numerator. And since we are going to write a rational number in its lowest form, GCD of a and q is 1. So exactly, now this is just technical. So you can just say the same thing, that if your q, so notice the value of this function essentially depends on the denominator q. So if the denominator q becomes very, very, very large, this function, the values of this function become very, very small. And that is why f contributes more at those rational points a by q with small denominators. Now, okay, that's good. So we have a nice technique to actually look at the values of the function at rational points. Now the other question is, how do we know that these rational points are the peaks of these functions? How do we know that these are the high performing points? So in a class of 100 students, how do we know that certain students are doing better? Well, for that, you need to know what is the average performance of the class, and then we check whether those students are performing above average. So this is what we are doing here. So we have to compare the average size of our function f of x on the entire interval 0 to 1 with these points at the rational values. Okay, so this is also like the fundamental theme in circle method, being able to specify. So some Ramanujan intuitively, when he first wrote his letters to Hardy, observed that at the rational points, functions which come from these exponential sums have very, very high values. That observation itself was a very new and fresh insight. And this was developed very carefully later on with Hardy once he moved to England. Okay, so now the question of average size of f of x comes out, right? So how do you calculate the average size of f of x? Because see, the closed interval 0 to 1 has infinitely many points, including irrational points. So what you do is you integrate the absolute f of x dx from 0 to 1, okay, and you divide it by the length of the interval 0 to 1, which is just 1, and this is basically your average value. Now you know that f of x is a complex number, and playing with absolute values of complex numbers can take very long and they become very annoying. So you play a very cheap trick. You square this, okay? So what we do is we try to evaluate the square of the average size of f of x. And then from that, we take the square root of whatever we get and we would say, okay, this would be the average size of f of x. So why does it help us to actually take squares? So now you're taking absolute f of x whole square, integrating it from 0 to 1, okay? And then you write, so this is your nice identity that comes from complex numbers, that the square of the absolute value is just the complex number times its conjugate. And then you have explicit values for these f of x. You have formulas, so summation. So this is a double sum over all the primes p1 and all the primes p2. So the first term e of p1x comes from f of x. And when you take the complex conjugate, your e of p2 of x just changes into e of minus p2 of x. So what you have is, you can, since these are all finite things, you can interchange the summation and the integral. So take the double sum over primes out. And then for each p1 and p2, you've got the integral e of p1 minus p2x dx from 0 to 1. And you know, again, from your integral evaluation of this expression, that this will take the value 1 only when p1 is equal to p2. Otherwise, this will just become 0. Okay, so there's only what you call in technical language diagonal contribution from these sums. So only those pairs p1 and p2 get counted where p1 is exactly equal to p2, which essentially gives you the total number of primes up to n. So what this tells you is that the square of the average size of f of x is approximately pi of n. I'm doing a lot of hand waving here, okay? When you start working out things in their entire technical detail, that constitutes the entire course. So the average size is approximately pi of n. Okay, and what do we know about the values at the rational point? Well, if your rational point a by q has a denominator which is not too big, then its value is pi of n, which is almost square of the average size. This is how we know that the rational points with bounded denominators are very highly performing values. Okay, so this you go on and you calculate the major arcs. So now at this point it becomes technical, but essential idea is you classify those rational numbers with bounded denominators, and you construct very short intervals around them, and these are your major arcs, and then the minor arcs are whatever is left behind after you take away the major points. Now, if you think about it carefully in terms of the geometry of the circle, The minor arcs essentially consists of the entire circle with just some points taken out. Okay, some very tiny windows taken out. And M consists of those tiny windows which you take out. But then when you evaluate the integral, you break it down into integral over the major part as well as the minor part. Okay, it is these small tiny windows around these rational numbers that give you the massive contribution. Okay, so what we do is we write our square of f of x in terms of the major arcs and the minor arcs. Okay, I know I'm running out of time, but I basically want to spend the last few minutes just at least explaining to you why this kind of an idea. So I'm explaining this whole idea to you to show you eventually why it doesn't work for the binary Goldbach. Okay, so you've got this integral, and it turns out that the integral over the major arcs gives the main term because f of x is very, very large, but the length of the arcs are small. And integral over the minor arcs gives the error term. Here f of x is relatively small, but the length of the arcs are big. Okay. And I'm doing some hand waving here, but those of you who've taken this course with me know that evaluating the integral over the minor arcs is the real deal. It is a very extremely intense calculation, and you end up using techniques from Diophantine approximation theory and exponential sums. But we don't worry about the technical stuff right now. Now the minor arcs for binary Goldbach. Okay, so you have square of f of x e of minus nx dx integrated over the minor arcs. Okay, and we just discussed that minor arcs actually consist of almost the entire interval 0 to 1. Okay, so if you are interested in an upper bound, what you do is you bring the absolute value inside the integral, and because of that, the e of minus nx just disappears. Okay, so you are just left with something which is absolute f of x squared dx. Okay, which is roughly of the same order as integral of absolute f of x squared dx going over the entire unit interval. Okay, the moment we get rid of exponential part, we are getting rid of the cancellations that happen. Okay, and once you have non-negative functions here, the essential thing to worry about is the length of the arcs. So this we already saw that this was approximately pi of n. Okay, so it looks like you have a value which is almost as large as the main term. Okay, so to get over this problem, what you do is you just keep manipulating and looking at this expression from different points of view. So once you take the absolute value inside, what you can do is you can bring one of the absolute f of x outside and keep the other one inside. Now, when you take absolute f of x outside, what you have to actually bring out is the maximum possible value of absolute f of x as x runs over the minor arcs. Okay, and this bit, so now what is happening is you've already shown that absolute of f of x dx integrated over the minor arcs is of the order of root pi of n. Okay, so if you want to get, and this minor arc is supposed to give you the error term, so to get an error term of smaller order, what you now, so your main term is of the order of pi of n. Okay, so what you want is that the right hand side here should be of order strictly less than pi of n. You are telling me that the integral part is contributing root pi of n. So you want this maximum bit to be of order much smaller than root pi of n. And this is crazy because what you are saying is, well, we want the maximum value of a function to be of smaller order than the average order. So you're saying that you want the maximum, the highest scorer in a class to score less than the average score of the class. That's nonsense. That cannot happen, right? And this is the reason why this particular approach also fails for the binary Goldbach situation. However, this idea of bringing one power of absolute f of x outside, it works perfectly fine for the cube case. when you take f of x cubed. So therefore, for the ternary Goldbach conjecture. So the circle method works very well for ternary Goldbach conjecture, but it is ineffective. Okay, it tells you for sufficiently large values of n, the integral can be shown to be positive. And so this is basically Vinogradov's theorem, which is a little more precise way of saying what I just said, that this integral f of x cube e of minus nx dx can be written as something which is of the order of n square plus an error term. So this is the contribution from the minor arcs, which is saving a small factor over n square. So the error term is smaller than the main term. Okay. And so yeah, so a quick remark before we conclude. Okay, so if you want to show, so this is fine. Vinogradov's theorem, very good. You can write it, you can write the integral as this formula where there's a main term and an error term. But how do you know that the right-hand side is positive? For the right-hand side to be positive, okay, you need to know what this O term, this O estimate means. What is the constant coming into the picture? Okay, and this is where, so what you know is, so if you tinker around carefully with that formula, you can actually show that for n suitably large, in terms of these constants that come into that equation, okay, your integral would be positive. But getting a precise hold on these constants is not easy. Okay, so this is in some sense one of the major contributions of Harold Helfgott's method. He also uses the circle method, but in a more involved and complicated way. But he's able to, in such a way that he's able to specify what are the constants coming into the picture. And therefore, he makes Vinogradov's theorem effective enough to give us the ternary Goldbach problem. Okay, so one final remark. I don't have time to delve too much into it. As I mentioned, roots of the circle method lie in a 1918 paper of G.H. Hardy and Ramanujan. It's titled Asymptotic Formulae in Combinatory Analysis. And this paper is also available on the internet if you want to go and have a look at what they were doing, something similar, but for the partition function. Okay. This partition function was also studied by Rademacher later. And in fact, now it is now believed that when Ramanujan, so if you go and check the letters, the original letters that Ramanujan wrote to Hardy, in one of those letters, he claims a precise formula for P of n. Okay, and after Hardy discussed this with him, after Ramanujan's arrival in England, and took this forward with Littlewood, now almost all scholars have come to the conclusion that Ramanujan did in fact have some form of the circle method in mind. But unfortunately, he died too young, and these methods were developed carefully by Hardy and Littlewood. And so unfortunately, now in many treatments, you hear of this method as the Hardy-Littlewood circle method. But we should not forget the original contribution of Ramanujan to this. Now, I'm going to, I had way too many slides to present. So I'll just conclude with a slide on resources for further reading or learning. So here are some nice books you can look at for this problem. So there's a book, the Trim series. It's brought out by Hindustan Book Agency. An Invitation to Modern Number Theory. I like this book a lot. It is like a problem book, basically. So they cover all major developments in number theory until recently, including concepts like random matrices in a very problem-solving type of a format. So just as Ramanujan learned mathematics by working on problems in Card's synopsis, you can take up An Invitation to Modern Number Theory and work through its problems. On the other hand, if you like, when you are learning something new and you like having things written out in front of you in a very precise theorem proof type of way, and there's totally nothing wrong in that, it's your approach to learning, then I recommend this book by Melvin Nathanson, Additive Number Theory, The Classical Basis. If you want to understand properly how the circle method is applied to the partition function, then I recommend topics in analytic number theory by Rademacher. And finally, Helfgott himself, other than, of course, writing papers on the topic, he has uploaded an entire book on archive where he develops the ternary Goldbach problem and his techniques from scratch. So if you really want to understand Helfgott's work, he has presented it all to you in complete clarity. It's available on archive. And there are two resources which are, now is the era of web seminars and web talks. So you can go to IMSE's YouTube channel, and there's a lecture by Professor D. Schnirelmann. So he explains the Hardy-Ramanujan formula, so the initial origin of the circle method as it was applied to partition functions. So basically the 1918 paper. And then the last one, so I don't know about you people, perhaps you are familiar with Dr. Seuss. I wasn't, it was new to me, but apparently he was an American children's book author. But famous enough that even college kids in US quote Dr. Seuss for, to sound cool and nerdy. So so Professor Stephen Miller, the same person who was mentioned, the first book, he himself has a YouTube channel, and he has given a lecture on Dr. Seuss and the circle method. So he actually dresses up as a character in one of Dr. Seuss's story, and he takes some famous poem which was written for children. I believe it's called Sneetch, and he just narrates the circle method in terms of that poem. So if you have a flair for the dramatic, then I highly recommend this lecture. So thank you for your attention, and I think I'll stop at this note.
So we have a question in the chat.
Okay.
So Mihir, is Mihir around? Yeah, Mihir, if you're around, then can you just ask a question?
So, ma'am, I had this question regarding the minor arcs and the major arcs that we construct.
This is a great question, Mihir. I just read it. So you're right. So this is a part that I did not go over much. So what happens is that if you have a rational value where the function takes very high values, there is a technical technique in number theory called partial summation, which basically tells you that irrational numbers very, very close to that rational number will also take very high values. So from a peak rational point, okay, also due to continuity of your function f, you can like spread over intervals in which a of q is contained, but those intervals should not become too large. That is a technical calculation. I did not go over it, but yeah, if the value, so it's like saying that if for example, if a Fields medalist is giving a lecture, so I'm not like, for example, if Harold Helfgott was giving this lecture to 2-3 people who are studying and learning the method carefully with him, they would understand it much better if I'm giving it to a class of 50 people, right? So that's that high. A over q is like a high performing. So in this case, the person who proved the theorem can think of him metaphorically as A over q, and you have a small neighborhood around it. Smaller the neighborhood, bigger the quality of the function. Sorry for the silly analogy, but hope you got the point.
Yes, ma'am. Thank you.
So Tanuj writes, I have that book, big fan. Okay, Riddhi has another question. When you computed f of half, you said it is approximately minus pi of n instead of exactly. Yeah, so yeah, for f of half, it is exactly equal to minus pi of n. There's no approximately there. The approximation starts coming into the picture when you start taking higher values of denominators. So that's right. If somebody else wants to ask a question, go ahead and ask.
So is Helfgott's proof the first complete proof of the ternary Goldbach conjecture?
That's right.
And so the ternary Goldbach conjecture doesn't imply the binary Goldbach conjecture, but does it provide some insights to how that would be proved? Or
No, not really, because the essential technique that has been used for ternary Goldbach conjecture, the essential insight it provides is that this will not work for binary Goldbach for the reasons that I just showed.
right.
Slides. For binary Goldbach, some very fresh new idea has to come.
Yeah.
So what we saw is was that you sort of talked about two methods. Like one was the Schnirelmann density method that you use, and the other one was this circle method. So
Yeah.
were there any other methods that were used to solve the Goldbach's conjecture, but then later we like there was some problem or something like
Yeah,
in like this?
that's a good question. But I think essentially all efforts to solve Goldbach's conjecture or other variants have used circle method in some form or the other. And that's why you'll see that most of the major developments, I mean, I could be mistaken it, but from whatever little knowledge of the literature I have, most of the developments came after this 1918 paper of Ramanujan and Hardy. In fact, they even came later. So 1920s, Hardy and Littlewood developed this method to provide more insights into the Goldbach problems as well as the Waring's problem, which I did not have time to talk about. And then the mathematical community caught on to this method that this approach is going to work for the Goldbach conjecture.
So we cannot like think of any random sort of way and like
Totally can. Why not? But I don't know of it. But who knows? Maybe you'll come up with something, some new way of looking at it. Keep thinking about it.
And to add on to that, okay, I go ahead.
Yeah, I had a question regarding one of the theorems you had talked about earlier, the Hardy-Littlewood theorem. So you said that it is conditional upon the generalized Riemann hypothesis. So are they proving equivalence between the statement and the GRH?
No, not equivalence. They are using GRH to prove that theorem.
Okay, so if GRH were true, then this is true.
The theorem is true. Yeah.
Okay, thanks.
Is that a valid approach to in general? I mean, can you prove things conditional to unproven things? And that, I mean, is that held true in the literature?
No, it's not held true, but it is considered. The value of this condition, the value of a conditional theorem is not as high as the value of an unconditional theorem, but the conditional theorem itself provides many insights. Okay, so this was the first result in this direction, and then other people came and observed the method carefully, and exactly at the points where the generalized Riemann hypothesis was used, they could think of some alternative approach which could get rid of that. So it is important in that sense. It provides a direction to the community to proceed.
Right. And to add on to Yash's question, so all the methods that you talked about were analytic in nature. So is additive number theory innately analytic, or are there other approaches to proving results in additive number theory?
No, there are many different approaches. I only explained certain kinds of problems and a technique which is quite big, very useful in approaching that. But generally, there are more algebraic approaches. For example, these big theorems like Fermat's last theorem, etc., they were proved using a very algebraic approach. In fact, a lot of algebraic geometry was also used in those proofs. That approach was different from what we would, in a narrow sense, classify as an analytic approach. So yeah,
and what about combinatorial approaches to additive number theory? Is that things that?
No, that is the latest. This is a new field which is gaining a lot of traction. Okay, with Terry Tao, James Maynard, and many others. It's called
Right.
additive combinatorics. So this brings together additive number theory and combinatorics together. Since
Right. I'd heard that Terensta was working on additive combinatorics, and when you said that you'd give a talk on additive number theory, I was like pretty excited because.
So in that case, I'm going to request you to give me a second chance. Maybe sometime next semester, I can give you people a talk on additive combinatorics.
Sure.
Yes, sure.
For it, yeah.
Like this is one of the very few talks in which, like, you explained everything so well. One of the very few talks that I actually understood.
Oh, thank you.
Quite a lot of stuff.
This made my day.
Yeah, this was not too simple, but also it covered all the bases, but it was understandable. So yeah, that's
great. Yeah, that's nice to hear.
So to add on to something that Varun asked earlier, I remember reading somewhere that Littlewood proved some theorem by first assuming that the generalized Riemann hypothesis is true, and then he proved it again by assuming the negation of the GRH is true. So that proves it unconditionally. I'm not sure if this is right or not, but
something is true when GRH is true, and then something holds even when GRH is not true.
Yeah. So you have two conditional.
This I can search it and maybe we can discuss this more over email. I don't know which result you're talking about.
Yeah, I don't know the name of the result either. I'll search around. But this I think this is an example of, I mean, if what I read is correct, then this is an example of how two conditional proofs can give an unconditional proof.
Absolutely. Yes.
right. Yeah. Ma'am, so can we get the PDF of the slides so that we can share it with?
I can mail it to you right away.
Sure. Thank you.
But it will have even more information than what we had.
Right. And the link for your talk, the complete talk. So
can you just give me 1 second and just share the link right away? Chat. So this is the link to my Gonit Sora talk. Okay. And I'll email the PDF slides to you. And whoever is interested, you can forward it to them, or you can other people can also write to me directly. I'll be happy to share the slides with you.
Sure. Yeah, I think I'll forward it. I think I'll reply with the PDF to the main email that I sent it to everyone. So.
Okay, you may not want to send it to everyone. Maybe that
okay.
to whoever.
Right. Okay.
Yeah.
Sure. I don't think we have any more questions.
Okay. So Riddhi has a message, very kind message. Thank you, Riddhi. And thank you all for your presence. Okay. So she has also suggested talk between connections between number theory and knot theory on YouTube. Yeah, that's great. Maybe other people can also explore this. Very good. So it was very nice to talk to all of you, and I'm glad we've started the math club meetings again. Thank you. Thank you to Aniket and Varun for your efforts.